Well, I'm using this clip-on microphone, which is not on a clip-on, but I'm holding it in my hand because the sound is recorded better like this. Anyway, this video is dedicated to Amit. Happy birthday. And today I'm going to try and explain a little bit about Newton's laws of motion. Isaac Newton was about 24 years old when his university in Oxford was closed due to the Black Plague. It was in 1667, and just imagine that you spend your summer break in a farm somewhere in England, and it was his family's farm, and what he chose to do on his summer break was to, as I see it, make some time for things that interested him. And it was there in these 3 months that he came up with his 3 laws that eventually were able to explain a lot about our world and apparently also about the universe, since larger items and or celestial bodies such as stars, they also move according to the laws that he discovered. I want to First of all, I want to present these laws accordingly. These laws are, let's say, they represent a model of the universe. These laws can and were modified as time goes by. We know that the model that Newton suggested is true for a certain size of bodies and a certain range of speeds. If we approach speeds that are close to the speed of light, then we have to modify these equations in order to represent better the movements of these very, very fast bodies. I'm saying it so that you will understand that when you use the term laws, it might have some kind of a deterministic meaning, and sometimes that intimidates people from understanding this is something that hopefully one day they would be able to challenge and maybe even to modify, because just putting them high on the shelf and calling them laws it's not good for science. If you want to really understand the laws, you need to understand that there were assumptions that were made and were very luckily proved to be true. But these are not laws. They are constantly checked and they're constantly subjected to be reapproved and re-verified. So you really need to check them and to know what they're talking about, since you someday maybe would find a way to improve them in the way that you will find a way to make them more suitable for a certain type and kind and range of physical characters. So let us start with a simple scenario just to make you understand what these laws represent. Let's say you sit at your home, you're watching television, you're what you call at rest, you don't have anything on your mind, you're just watching TV, your favorite series or your favorite game on the Champions League. The maximum thing that you do is that you move in a constant velocity to the kitchen to grab something to bite and back to the couch or wherever it is you are, and that's it. No interference, you're totally at rest, everything is good. And then you hear a phone ring. That is represented as an interference to the steady state that you were at up until the moment the phone rang. You respond to that interference by creating a movement towards the phone. and let's suggest that the phone is not on mute, and let's just not suggest, assume that the phone is not on mute and that you are expecting a phone call. And now the rate of the change depends on the magnitude of the interference, meaning who is calling. If it's someone from the lottery that you sent a form in the morning and you have a chance of winning the lottery, and in your country or wherever you are, winning the lottery is informed by phone, there's a good chance that you will even run to the phone. But if not, there is another option. Maybe it's just a regular phone call, then you'll just walk to the phone, no running needed. The rate in which you respond to the interference is important in the aspect of the situation, and I'll explain later how it relates to Newton's laws of motion. Lastly, when you reach the phone and you answer the phone, your reaction to the action that the other person on the other side of the phone, the things he says to you and in the manner in which he speaks, they are related. Meaning, if someone talks politely to you, you talk politely back. If someone talks in a slightly agitated state in an agitated manner, so you can react accordingly, maybe with more force, with more assertiveness. It's interrelated, and I don't know if I just made up a word, but it's interrelated, but it's related. It's the way you react corresponds to the way you are reacted. This scenario, which I think could be considered like an everyday scenario, an ordinary scenario, that is actually a representation of the three laws that Newton Newton phrased, or how do you say? This is an everyday representative of Newton's three laws of motion. How? The first law says that every body, unless it is interfered by forces, will be in one of two states: either at rest, meaning zero velocity, or moving in a straight line in a constant velocity. Okay? That is Newton's first law of motion. It gives us some kind of base, a point of reference to be aware of. If you have an interference, meaning you have a force acting on the body will react by creating acceleration that the rate of the acceleration corresponds directly with the body's mass. If the body has a lot of mass and the force is constant, then the acceleration will be small. If the body is small and the force is constant, the acceleration will be big. And that is where Newton actually, he also took a major role in the formation of the derivative and calculus, and these were actually tools that he needed in order to create this model of movement of bodies. Not something that some students presume that it was specifically made in order to torture them and to make them miserable by creating all kinds of terms that are just sometimes seem ununderstandable. No. Newton did this in order, he had a point, he had some sort of bottom line that he wanted to be able to express better, so he needed these calculus elements in order to express his notions better. And it works, because we know from experiments that this is how bodies do behave. The last law, which is the third law, talks about an action and a reaction. If I exert a force on the table, I don't know which one you can see, okay? Let's say I'm pushing the mic, okay? I push it in the same force that the mic is pushing me. The difference is that the direction of the two forces is opposite. And that is important, since if we take, for example, the Earth, who do you think attracts each other more? Do I attract Earth the entire Earth more, or does the Earth attract me more? The maybe what seems to be an intuitive answer would be, well, of course that the Earth is pulling you more, but actually the answer is that we are pushing each other the same. It's the difference in mass between me and the Earth that it can explain the difference in the outcome of this interaction. Since my mass is way smaller than the Earth, I am pulled to the Earth rather than the Earth is pulled to me. The Earth does move as a result of the force that I'm exerting on it, but since it has a very large mass compared to me, its movement is very slight. Let's take, for example, a proton and an electron. They both have they both share the same electric charge, and we haven't talked about it, I know, but the same electric charge means that they have the same electric force that's pulling them, but the proton is something about 1,800 times more heavier than the electron, and that's one of the reasons that the electron orbits the proton and not the other way around. I hope you understand now a bit more of Newton's laws of motion, and above all, I hope it made you a little bit more interested regarding the subject, and that's it for now. Have a nice day.